Okay, I'm going to be talking about the Bach periodicity theorem today. And let me begin with a quotation from Atiyah in his obituary of Bach. So his announcement of the periodicity theorem transformed algebraic topology forever. Quoting from Atiyah, "This paper was a bombshell. The results were beautiful, far-reaching, and totally unexpected." The totally unexpected is really the point to make. There was no intimation that this was going to be true. So in briefest form, the theorem says that if you look at BU cross Z, this is just a discrete space put on to make periodicity absolutely correct. This is homotopy equivalent to loop 2, BU cross Z. So totally periodic. And BO cross Z is homotopy equivalent to loop 8, BO cross Z. One can imagine in retrospect how people might have stumbled on the first one. But the second one, the method of proof that Bach came up with, is crucial. Without that, you don't have the intuition as to what should be true. And so I'm going to do several things. First, I'm going to just give a very brief bullshit sketch. And then I'm going to give a sketch of Bach's original proof. And then I'll give a more modern proof that is from more concise. And you can check the details. So I'll explain how the proof goes without filling in the details. So at the time Bach started working on this, it was a published result that the 10th homotopy group of SUN for n large is Z mod 3. Do I have that right? Yes. And that was published result. My advisor contributed to that. It was also claimed in a paper that was not yet published that the same group is cyclic order a power of 2. Now, one of those two things is false. And Bach took it upon himself to figure out what was true, and in the process he developed this entire beautiful theory of using Marston Morse's theory, Morse theory, that was then 30 years old, in a totally new and unexpected way. And it's not just applying Morse's theory. He had to extend it considerably. He's very modest about it in the paper, but there's a lot to it. Okay, so the original proof, very briefly, just starts out with the obvious. You look at S2n minus 1, and that's homeomorphic. Let me get the numbers right for a change. UN modulo UN minus 1. So everything is about homogeneous spaces. Homogeneous spaces are throughout his way of thinking about this. So this is true because if you look at a point on S2n minus 1, say 1, 0, 0, 0, 0, UN acts freely, and UN minus 1 fixes that point, and so not freely, transitively. And so since UN acts transitively, there's only one orbit, and since the isotropy group at a point is UN minus 1, that's what it is. Okay. So we have a fibration, UN minus 1 into UN into, well, a bundle. We haven't talked about fibrations, really. This is a bundle. Has a long exact sequence of homotopy groups. We know that pi k SQ is equal to 0 for k less than q. So this is just repeating the obvious. The conclusion from just this much is that pi k u of n is equal to pi k of u. U is the union of all the unitary groups, right? For k over 2 less than n. So it doesn't matter what the precise estimate is, but that happens to be correct. Now, we've looked lots at the Grassmannians, but it's essential to Bach's point of view that we don't look at the Grassmannians precisely as we have been looking at them, but rather symmetrically, so that we look at n planes in complex 2n space. Very essential. Thinking of Cn plus Cn and thinking of n planes in Cn. And this is homeomorphic to U2n modulo un cross un. Okay? And somehow we've managed to go this far without ever mentioning the Stiefel varieties. So we've talked about the tautological n-plane bundle, but we've never talked about the associated principal bundle, where the fiber is the unitary group. And that's given by VNC, I guess I want 2n again. This is n tuples of, what's the right word, orthonormal if we were orthogonal case, but together n tuples of vectors that span plane. So these are the frames which give bases for planes. And so you map basis to the plane that it spans. And this is a bundle with fiber now UN. Okay? Okay, we can think of this guy as U 2n modulo UN, or UN cross E or E cross UN, whichever way you want to think about it, going into U2n modulo UN cross UN. And so the fiber is indeed what I wanted to say, right, whatever. By the way, the notes are already online. So if everybody wants to check out details, and where I don't have the notes online, there will be some of the results as I give them are in more concise. Okay. Less interruptions today because I want to cover it. But go ahead.
The VN looks like the permutation form. There is any relation.
I don't want to get sidetracked because I want to cover a certain amount of material. Right? You have, obviously, you can put the symmetric group inside the unitary group, but so what? It's not relevant. I mean, there are things for which it is relevant, but not today's talk. Okay. All right. The essential point is that we now get that pi k minus, this is not the essential point, but this is still preliminaries, is isomorphic to pi k of Grassmannian n C2n in a range of dimensions. Okay, so it's actually 1 less than or equal to k, and I don't give a damn what the upper estimate is. Okay, that's preliminaries. Now, in a sense that I'm going to sketch, Bach showed that this Grassmannian up here is the manifold of minimal geodesics in loop SUN. And the words maybe made absolutely no sense to you, but I will try to wave my hands at making sense out of them. And by Morse theory, you can conclude from that that loop SU2n is homotopy equivalent to a space obtained. This is just pure Morse theory, no algebraic topology at all. Union cells of higher dimension. So what do I want to say? Cells of dimension at least dimension 2n plus 2. Okay? And you see what that says on homotopy groups. This is Morse theory. This is pure differential geometry, no algebraic topology at all. And it says that then pi k, well, I'll skip trivial steps. Once you know this, you know that pi k minus 1 is isomorphic to pi k plus 1 of u of n. Just put things together and out that comes. Again, for n large relative to k. And the isomorphism is realized by a map. Okay? So that's the brief sketch. And the question is, where did this come from? And is it part of a general picture? This doesn't tell us anything, not even a hint, as why real Bach periodicity should hold. And the amazing thing is that Morse's original proof is so incredibly general that the Freudenthal suspension theorem for spheres is the easiest special case. What that has to do with this kind of periodicity should be completely, utterly mysterious at this point, right? There should be no obvious relationship. So, do I want to say more? Yeah, over the later years, many, many other proofs have come about. There's a proof, well, the periodicity itself, especially the real periodicity, is best seen in a periodicity phenomenon for isomorphism classes of modules over Clifford algebras. Those purely algebraically manifest an eightfold periodicity, and it's extremely explicit. That's in a very basic paper by Atiyah, Bott, and posthumously Shapiro. And it was later realized that you can actually realize geometrically that algebraic periodicity using Banach algebras. And that was done, that was in the air. Everybody knew it could be done. It was done independently by Wood in Manchester, I believe, and by Max Karoubi in Paris. So that's a proof by Banach algebras realizing the Clifford algebra periodicity. There's a proof by direct algebraic topology. You simply write down maps, explicit maps, compute on homology to prove that they're homotopy equivalences, and you just write down everything. That proof has the benefit that it tells you everything you want to know about the homology and cohomology of all the intermediate spaces. There are two early published proofs along that line. One was by Dyer and Lashoff working here. The other was by John Moore, my advisor, written up by Henri Cartan in one of the early Cartan seminars. And the fun thing is you have to prove 6 different equivalences for the real periodicity. And those two sets of authors found difficulties in different maps. And so you combine the easiest parts of their proofs, and it's really quite elementary. And that's going to be in a book that I'm writing right now on characteristic classes with Bob Bruner and Mike Catasando. Anyway, there's a more modern proof, actually just a couple of years ago, by, what are the names? I'm going to blank on this. Yeah, I want the predecessors. Aguilar is one of them, and Prieto, that's it. Aguilar and Prieto, they're two Spanish mathematicians. They gave a proof just using something called vibrations, which are like vibrations up to homotopy. And they just wrote down basically Bach's maps and just checked by quasi-vibrations that they get equivalences. So that's a homotopical version of Bach's original proof. So there are many, this is a great theorem. It should have many proofs, and it does. Okay, so I'm going to be talking a little bit now about Bach's paper called The Stable Homotopy of the Classical Groups. And this is 1957. It's really, really early and unexpected. And you start with a general symmetric space. Well, what is a symmetric space? It's a special kind of homogeneous spaces. Not all homogeneous spaces are symmetric spaces. But you start with compact connected Riemann manifold. So Riemann has already been advertised in this series of talks. If you want to know about Riemann, there are historical writings about him by Narasimhan, Raghavan Narasimhan, who was here for many years and a real scholar, and the history of his contributions is beautifully written up. Right. Such that for every point P in M, there is an isometry of M. What is my notation? There's absolutely no uniformity of notation for a general isometry. So I'm going to call it iota P for isometry, such that iota P fixes P, and it's symmetric. And the symmetry can be said by saying this differential is the negative of the identity map of the tangent plane at the point P. So it means it reverses geodesics, and it means that geodesics can be extended, so it's a complete Riemannian. Yeah. Right. It's good, it's nice, it's got all sorts of symmetry. Bach's idea of a base point looks nothing like our idea of a base point. But for him, a base point is a triple. P, Q, and H, where you've got 2 points on M, P and Q, and a homotopy class of geodesics connecting them. Okay? So H is a homotopy class of paths, geodesic paths. Okay? And H is one homotopy class of those, yeah. The trouble with this talk is to explain the definitions in detail, especially the next one, would just take us way too far afield. What?
Just say it again. I want to try. What's the point of it?
Okay. First, the point of a base point.
No, whatever. What did you want to do?
Just to share it again.
Right, and you've got a isometry. So you're looking at the group of isometries of M, and you want a symmetry on them so the geodesics are reversed. Think about antipodal points P and Q on the sphere and geodesics between them. So you've got one for each longitude line from the north to the south pole. And you're looking at a homotopy class of those, but the sphere is simply connected, so there's only one homotopy class. So for that point, from the point of view of a sphere, you would just take a pair, the north and south pole, say, and there would be only one homotopy class. And we're looking at paths from P to Q. The reason is that you want to look at where these paths, where geodesics sort of split along Jacobian fields. And I don't have, there's just no way I'm going to define Jacobi fields. The idea is that right. So let's let S be an arbitrary geodesic from P to Q. Okay, just any arbitrary geodesic from P to Q. There's a number called the index of S. And this is the number of conjugate points of P in the interior of S. So you have this geodesic going from P to Q. And you look at pairs of points where there's a Jacobian field that vanishes at t equals a and t equals b. You count the number of those points that appear. By the way, there's a very leisurely account of what I'm trying to, stumbling over explaining, in Milner's Morse theory book. And he gets to symmetric spaces on page 109. So he develops requires a fair number of preliminaries to get any kind of serious feel for this, which I quite honestly don't have, as should probably be quite obvious. But I want to just give the idea. So you count the index, and then the multiplicity, you have to count properly with taking account multiplicities. I'm not going to tell you what they are, but you have to count the index in a good way. And then Bach writes nu for the first positive integer, which occurs as the index of some geodesic from P to Q in the class H. So that's a number. Now, let me state Bach's theorem. This is the main theorem of the paper before you ever mention classical groups at all. So M is a symmetric space. Then, for any base point, and remember a base point is a triple like this. And Bach calls a base point nu. Oh shit. Excuse me. M nu. I meant to define M nu first. M nu is the set of all geodesics of minimal length which join P to Q and are in the homotopy class H. Right? So you look at your base point and you look at paths from P to Q, okay, of minimal length and in the homotopy class H. So that's a new space. Good. But it is a symmetric space. Okay. Right. I'll say a little more. I'll come back to that. Okay? You can't be, but all right. Right. What I want to say is there's a map from the suspension of m nu into M. And it induces a map nu star from pi k symmetric space sigma m nu into pi k m. Okay. What is this map? You think of a paths from P to Q. You're going to take your suspension coordinate to be going from P to Q. And you look at the map that sends a pair pair S and time t, just to S of t. That is, you think of a geodesic as a path in your manifold, and you evaluate it at some time t. Yeah?
Just to make sure I understand the definition of conjugate points, we're traveling along like two geodesics.
It's not as naive as that. I really don't want to explain. You'd really have to do some analysis. You have to define the Jacobi field, and then you have to look at points where the Jacobi field vanishes. And when you have a pair of such points, you say they're conjugate. Okay, so there you're looking at points in the interior of the geodesic. Look at where the Jacobi field is 0, and if you have a pair of such points, those 2 points are conjugate. Yeah, go ahead.
Just 2 words for you. There's sort of 2 separate things going on, and it might help to separate pick them apart. So one, you're trying to understand some space of paths. The reason is because you're interested in a loop space, which is that's some big thing. And the way that Bach chose to understand it after Morse is you can pretend that there's this nice function that like measures the energy of a path if you're a physicist. And you can take this big complicated space of paths and you can break it up into pieces corresponding to when that energy has a critical point. Right? And that's Morse theory, so that's step 1. And then that space is still too big, and so you want to make it smaller, and there's a nice subspace of the space of paths, which is the space of geodesics. That's easier. Those are the 2 pieces that motivate this kind of.
So remember, we have this number that is measuring the dimension of dimension the dimension of the vectors. No. So this is the first positive integer, which occurs as the index of a geodesic from P to Q. So that number should seem totally, where does it come from? How do you calculate it? And this is the extension of Morse theory that Bach develops, that is the force of the paper. There's a method of computing that number. But here's how he uses it, and here's the conclusion that he gets. Namely, this homomorphism nu star is a surjective in dimensions less than nu, and bijective in dimensions less than nu minus 1. That should look, hey, that's looking like the sort of thing that Freudenthal suspension is trying to tell you, right? So, as Bott writes, at first glance, the evaluation of the nu, the absolute value nu, may seem a formidable task. But then he explains why it's really routine, at least to him. He was a very modest man. He's absolutely brilliant, but really he's also one of the nicest human beings I ever met. He's just a wonderful person. His paper, it shines through. You almost don't see the depth of what he's saying because he's so modest about it. but it's just incredible mathematics. And he's using something called flat tori in the relation they hold to Morse theory to evaluate this number. And there's no way I'm going to even try to explain that because I'm just not expert enough. And the paper is very dense. It's well written, but you have to have complete background, the first 109 pages of Milner, to really appreciate what's going on. Okay, so in interest of time, I won't go through Freudenthal suspension, but the idea is the example that I wrote in answer to his question, that you look at the sphere, you take antipodal points, it's a consequence of the definition of symmetry that any 2 points on your manifold can be connected by a geodesic. And that from there you see that the group of isometries of the manifold acts transitively, okay? So, and that you proved is compact Lie group. And the isotropy group of a point is a subgroup. And so your manifold is homeomorphic to a homogeneous space, G mod H, where G is the isometry group, and H is the isometries that fix a given point. Okay. So, if you apply, I'm not going to give details. If you apply this to a sphere, out does come Freudenthal suspension theorem. That is exactly the right estimate. It works. So what Bach does then next is the point of this lovely thing, this is a symmetric space. So I can do it again. Do the same construction to M nu. And do the same construction to M nu nu. And keep on going. And you get a new series. And from the new series, you start calculating. And these are, classical understanding of classification of what these symmetric manifolds look like. So you can just, if you're a good geometer, figure out what spaces you're looking at.
Here, I think it's not the maximum suspension.
What?
I think you need to adjoint to that. M nu is an approximation of the root.
I wrote what Bott wrote. That's correct.
So M is a sphere.
Freudenthal suspension we wrote down,
Yeah. Okay.
right? Well, oh, I see what you're. Remember, M nu for the sphere is the sphere of one lower dimension. Well, did I write something wrong?
M nu is a sphere is definitely multi-dimensional.
Yeah.
And what's the sphere with lower dimension of that theorem?
Wait a minute. Wait. I'm sorry. That's what you want.
But then I want to or shift. Okay, but you're good.
No, this is correct.
Okay.
Right. The unless I've got a typo here. Right? We certainly have a map from the suspension of M nu A into M.
The adjoint goes to M nu.
Right. So you're right. I guess so. This should be pi k plus 1. This is probably a typo. Okay, yeah, it's a typo. I apologize. This is the map that you want to stare at. And if M is an n sphere, M nu is an n minus 1 sphere, and this is pi k of the n minus 1 sphere going into pi k plus 1 of the n sphere. Right. Another question? All right. Bach starts calculating, and he sees that the Grassmannian that we know and love is mapping into U2n, and the number nu is, this is M nu, and the number here is 2n plus 2. And then there's O2n modulo On cross On, and that maps with n plus 1 to U2n modulo O2n, and that maps via number 2n plus 1 into symplectic 2n, another typo, U2n, and that maps into 4n plus 2, symplectic 2n. And then you start over with symplectic 2n modulo symplectic n cross symplectic n. So we should think of this when n goes to infinity as the classifying space of the infinite symplectic group, right?
Sorry, the cross product on the bottom of the chart.
I'm sorry?
You've got symplectic 2n quotiented by symplectic n cross.
I can't hear you.
You have symplectic 2n quotiented by symplectic n cross symplectic n.
Yeah.
Is it on the bottom or the top? Should there be one?
This is related to this by loops. Loops of this is that. So when you're looking at an obvious relation, he doesn't write it down. Let me keep going. 4n plus 1, u 4n modulo symplectic 2n into 8n minus 2, SO 8n modulo u of 4n. And this part of the argument for Bach is just, oh, this is so routine. You almost can't bother saying it in detail. This is a 3. This is a 2. Right. SO 8n. Okay, and then the loops on this is that. You put it all together, there's eightfold periodicity. Now you try to get that by sheer intuition or guesswork or knowing the homogeneous space. There's no way you're going to guess it. So this is the way the proof theorem had to be proven. You just could not possibly see the intuition, I think, without this. But in retrospect, you can see why this is plausible and see the maps. And as Dylan was indicating yesterday, Atiyah and Hirzebruch had defined K of x, and they wanted the tensor product with the Bott class to be an isomorphism. And they couldn't prove that. But they did know at this point, they had just heard the Bott periodicity theorem. This is all going on in an incredibly short span of time. You have to remember, there was no email, and people were not in the same place. It's incredible how fast things went. But Atiyah, asked Bott if it could be true. And there's this lovely paper, I was advertising at the end of Dylan's talk, in the English translation, we see some points about the periodicity theorem, where he says, okay, some people don't like all this Morse theory. I'm going to write down the maps explicitly, and I'm going to check from this explicit description of the maps, the maps giving the twofold periodicity are given by multiplication by a Bott class. And the map, much harder, that the map given by multiplication by the Bott class of dimension 8 is an isomorphism in the real case. That's not easy. That's because you're dealing with a sequence of maps and you're trying to distill that information to get out an explicit map. I don't know to this day a really clean proof of the eightfold periodicity given in the form that we know and love. Right? You can't just do glotching functions. So later on, Atiyah gave the proof of the complex periodicity using clutching functions that probably anybody who's looked at his book or other sources will have seen. So there is a kind of quite elementary proof by analysis. But that came later, in 1963. This was, after the dust had settled in some sense. So, what time did I start? About 9:15. So everybody comfortable with the connection between this and what Dylan was saying yesterday?
I got a little bit off there. What about the numbers that you're writing there?
These are the absolute values for nu, right? At each time I'm looking, this is m and this is m nu. This is m nu. And this is the corresponding value of the nu, the absolute value of nu. Okay, so the first place something happens in the Morse theory construction. Okay? So this is very far from the kind of mathematics that algebraic topologists do. And even at the time, Morse theory was 30 years old, and most experts did not actually know it and had not assimilated it. Bott was really writing to try to resurrect, in some sense, the theory because he needed it. Okay, so the idea is that you want a completely explicit map that builds the equivalence, and you want okay.
At this point, we haven't said at all what the relationship is with X and space.
That's what I'm about to do.
Okay, great. Okay. Sorry.
Right. Is Ben here? Yeah. Am I stepping on your toes? I have no idea what you're planning to talk on.
Oh, I was planning on talking about K theory.
Right. So he jumped the gun yesterday.
Repeat it, so.
Right. And this is so basic that you should. What?
Let's not worry about it. We'll do it.
Okay. So, yeah. What is the relationship between K theory and these spaces I've written down, right? So Dylan defined K of X is the Groton deconstruction on vect X. So you're looking at vector spaces up to isomorphism of any dimension over X. X is compact for this purpose. And you make this into an abelian monoid by direct sum. That is, if you have two bundles over X, you take the fiberwise direct sum, and that gives you another vector bundle over X. That gives a monoid structure on it, and you make it into a group. But now you remember that X BUN is isomorphic to vect n of x. This is the classification theorem that we've seen in a fair amount of detail, right? There are many proofs of this as well. Proof that I particularly like that is very different from the classical proof. But anyway, let's accept this. One technical point that you have to emphasize. In my first lecture and in a number of lectures, brackets has meant base point preserving maps. Over there, when we talked about the definition of homotopy groups, it meant that. And this does not mean that. This means unbased homotopy classes of maps. So if you wanted to make it into based maps, you'd give this a disjoint base point and write it that way. And then your brackets mean homotopy classes of based maps and everything is consistent. Okay? And the difference is going to matter in a moment. So this map is given a bundle C over X. There's a particular virtual bundle over S2. And you tensor those together. The tensor product extends over the Groton deconstruction to give a ring structure on K of X, and you can multiply. So we get a map, and multiplication by the Bott class is an isomorphism. That's the version that Atiyah and Hirzebruch wanted. Okay? So this is true. So we can think, if you like, of X plus and BU cross Z. What's the Z doing? It's recording dimension. So if you have a virtual bundle, you have the, it's a difference of two bundles. You take the difference of the dimensions, and that's a number. And that's what's giving the coordinate of the Z coordinate of that map. And the BU coordinate is giving a stable vector bundle. Remember, normal bundles are stable? So they have the same classifying map up to mapping BUK into BUK plus whatever. So it's a map like that. So these are X. If you write based maps into BU, where this is the zero component, BU cross Z, zero, that is stable homotopy stable classes of vector bundles, where two bundles are equivalent. If when you add a trivial bundle to one and a trivial bundle to the other, you get equivalent bundles. That's what that lower thing calculates, XBU. Okay? And there's another name for this. This is the reduced K theory of X. Okay? And there's another version of this, reduced version, which K tilde X tensor K tilde S2 maps isomorphically to K tilde of X smash S2. So that's the double suspension. Okay? But now this is represented, so that this is looking at, let's put it up here. So looking at this, we were looking at, down here, maps from X into BU, tensor maps from S2 into BU if you insist, but we're going to pick one particular map given by the Bott class, the particular bundle. It's H minus 1, where H is the canonical bundle, line bundle, into sigma 2 X BU. And this is given by, if you have a map from X into BU, well, let's put more general Y for the moment, because it's clearer. If you have a map from X into BU and a map from Y into BU, you just take their smash product together, and that'll give you a map from X smash Y into BU smash BU. And then you have to know that there is a multiplication here that is given by tensor product of bundles. And that makes sense because BU there really means BU cross zero, the zero component. And the base point is the trivial bundle, and the tensor product of the trivial bundle with the trivial bundle is the trivial bundle, so it factors through the smash product like that. And this composite is this pairing from there to there. Okay? I'm sorry?
That's the X and Y BU set.
This is this pairing of Jarian.
Yeah, so that's
Right. You're going ahead to the next step, where we specialize y equals S2. And then what we're seeing is that we're looking at x and y, going to x smash y. So we're looking at x BU into sigma 2 x BU. I'm taking y to be the 2-sphere, okay? And I'm taking the particular class called the Bach class here, particular bundle that actually, the second homotopy group of BU is Z, and you're taking a canonical generator for that homotopy group, and you're multiplying by that canonical generator, okay? And so up to homotopy, this is represented by a map from BU into loops to BU, right? This after all, is x into loops to BU. And there's a quibble here that x was compact in the interpretation, and we want to apply the identity map from on BU to get a map from BU into loops to BU, but that's a quibble that you can sweep under the rug. There's a lim1 vanishing that is relevant. Anyway, that works. And so this corresponds to a map, this pairing. And what did he and Hirschberg wanted was this to be an isomorphism, and that's the same thing as saying that's a homotopy equivalence. And so that's a map given, and Bach gave a totally different map, and you had to show those two were homotopic. And this is what this paper that is never referred to of Bach's does. And it's not obvious, and it's particularly in the real case, it's serious work to prove that. And the incredible thing is the two papers, the Annals paper where he proved Bach periodicity first, and the paper in response to Atiyah, those appeared in the same year. It's just incredible, given that they weren't even in the same country for part of the time. It's just, the speed at which things were going in this period was just really quite unbelievable. So let me pause and ask if there are questions. Yeah. Because this is maps. Remember the very first lecture, I emphasized sigma x, y is isomorphic to x loop y, right? This is, implicitly or explicitly, we've been using that every day. It's really, really important. Okay, now that answers that. Okay. So, where? Oh, yeah.
So, can you make the same argument if you do real K theory, you just have to do S8 instead?
Yeah, but the point is you don't have one map, you have a sequence of maps.
Okay.
And you have to be real careful to see what that sequence of maps comes out to in the end. So there's, it's not easy. And that paper is not easy reading. Perhaps that's why it's so seldom referred to, but it really deserves advertising. It's a lovely paper. Let me just write down the bot map explicitly. So here's how the proof would go by old-fashioned, no, not old-fashioned, our way of thinking directly. Does everybody see how things fit together with Dylan's motivation leading up to how this was used? To understand Riemann rock and modern developments that stem from it, needed Bott periodicity. It was just like incredible. And I think Ben will talk about K-theory as a cohomology theory. Are you going to talk about that? Okay. So this K of x was just one value, but it is the 0th value of a cohomology theory. And that's an immediate consequence of Bott periodicity in a way that Ben will explain or else I will explain tomorrow, but it's just absolutely immediate. And that insight revolutionized algebraic topology. Remember Steenrod, I knew Steenrod was one of my mentors when I was a graduate student. And he said he was away from Princeton in 1960. And when he came back, he didn't understand a word that was going on because generalized cohomology theory had been invented in the 59 and 60, coming from Bott periodicity. So let me write down the Bott map explicitly. And you'll see if in staring at it, oh, there's some symmetry going on that you can just sort of see the remnants of the original ideas using geodesics in the explicit map that Bott wrote down. So let me first outline this sketch of the proof. Cohomology of BU. You've seen talks on cohomology of BON. It's the polynomial algebra on the Stiefel-Whitney classes W1 through Wn. Go out to infinity, it's a polynomial algebra on Wi for all I greater or equal to 1. But the Whitney duality says that there is a diagonal map on cohomology of BON, which you saw and took as psi of WK is summation I plus j equals k Wi tensor Wj. Okay, that was explicit in Jolie's talk, right? And the unitary group works exactly the same way. This guy is a polynomial algebra, but now Z, integer coefficients are understood throughout, on Ci, where I greater or equal to 1, and now the degree of Ci is equal to 2I. Okay, and now we have exactly analogous formula. The psi of Ck is summation I plus j equals k of Ci tensor Cj. And that comes from the same reason. The Chern classes have this property on sums of bundles that is precisely analogous to the properties that Stiefel-Whitney classes have on sums of bundles, and that gives that formula. I should say there isn't a homotopy invariant definition of this Chern classes analogous to the definition of Stiefel-Whitney classes by Steenrod operations. You do not have that kind of simplicity going on. But nevertheless, the algebra looks exactly the same. Hopf in 1940 introduced the notion of an H space, a space with a product with a two-sided homotopy identity element, and implicitly also introduced the notion of a Hopf algebra. It's exactly something that's got a product and a coproduct, but they have to satisfy some relation. And the relation is very simple. If you have the tensor product of two algebras, that's an algebra, right? You take A, B, and A prime, B prime, and switch in the middle and get A prime and B prime. Well, in a graded world, you have to introduce a sign, but it's exactly the same. And the consistency that defines a Hopf algebra is that the coproduct is a map of algebras. And if you write that down on a piece of paper, you see that that's exactly the same statement as saying that the product is a map of coalgebras. So that's the notion of a Hopf algebra. And this Hopf algebra and the Hopf algebra cohomology of BO have the incredible properties that they are self-dual Hopf algebras. If you look at the dual Hopf algebra. So that's the homology of BO and the homology of BU. They turn out to be abstractly isomorphic as Hopf algebras to their own cohomologies. The self-duality is a beautiful result, again, of my advisor, John Moore. It's in more concise and gory detail, and it's just a beautiful piece of algebra, but it's there. So let's accept this. The proof gives you that the homology of BU is a polynomial algebra on generators gamma sub I, where I greater or equal to 1. And those generators are very explicit. You look at BU1, alias CP infinity. Okay? And we have BU1 embedded in BU, right? It's the union of the BUNs. And so we have a quotient map from the cohomology of BU into the cohomology of BU1, right? Induced by the inclusion. Dually, we have an embedding of the homology of BU1 into the homology of, I didn't turn the arrow around. I did in my mind. Okay, turn the arrow around. And the gamma I, you take the basis elements, canonical basis elements, namely C1 to the I, and take the dual basis, and the dual basis elements, let's call them gamma I, and these give the gamma I that generate homology of BU. This comes algebraically out of the proof of self-duality. Okay? So that is a very explicit description of the homology of BU. So what Bach does, or how we reinterpret what Bach did, is this right? Yeah. You look at BU, and you look at loops SU. That's what you need to do because you want this to have the right homotopy groups at the bottom. So you write down a map like this. You look at homology of BU, and what you do is you prove that the homology of loop SU is also a polynomial algebra. Where under this map, let's call it beta for Bach, beta of gamma I is congruent to delta I mod decomposable elements. Right? Once you know that, you know that beta is induced in isomorphism on homology. These are H spaces, and that's a map of H spaces. And if you have a map of connected H spaces with isomorphism on homology, by God, it's a homotopy equivalence. Homotopy type of CW complexes, blah, blah, blah. It's enough. That's what you need to prove Bach periodicity. So let me quickly write down the map. Right? I have to write down this map beta. I'm going to quickly erase this part of the mathematics that I stumbled over. And get to the part that I really understand. And, right. We look at paths and loops of length pi, not 1. That's convenient. And I'm going to abbreviate V to the n is C infinity to the n, because otherwise I have to write too much. That's an abbreviation. And I'm going to define, I'm going to write BU as U of V squared modulo U of V cross U of V. So it's the union of, U2n modulo UN cross UN. And I'm going to think of SU, special means determinant 1, matrices, unitary matrices of determinant 1, as SU of V squared. Why not? They're all bold-faced in my notes. Anyway, I'm going to define beta first from U of V squared into U of SU of V squared. And the map is blindingly explicit and elementary. You take an element of there, linear transformation, unitary transformation, and you apply it to theta, where theta is between 0 and pi, is just the commutator of t and nu of theta. That's it. So that's t nu of theta, t inverse nu of minus theta. So where nu of theta is of z prime and z double prime is just e to the I theta, z prime, e to the minus I theta, z double prime. Okay? Now you got to be brilliant to understand why that's just the right thing to do. But you see that if you restrict to a t that happens to be of the form t prime cross t double prime, remember I'm using 2 copies of C infinity, then, hey, on each factor I'm just multiplying by a scalar, so the commutator is trivial. So everything goes to the base point. Therefore, this map, let's write it more legibly, factors through U of V cross U of V. Hey, that's a map on the Grassmannian. This is all. What have I done? I transposed letters. Does that look better? Okay. That's it. That's the bot map. Okay? And you have to check it's a map of H spaces. I don't have time to write down the H space structure. But this map, jumping ahead 20 years, is a typical example of a... What? Am I over time?
Yeah, you buzzed
In a minute. Okay. All right. Starting with this definition of the bot map, you construct a commutative diagram by restricting it to get a CP infinity into loop SU. That's a map, damn it. And you look at BU, and you look at loop SU, and you look at loop, this is a map J given by inclusions where you look at the first coordinate versus the second coordinate in my 2 copies of C infinity and use one of the coordinates to embed CP infinity. Okay, you get that. You look at it geometrically, and you look at its adjoint, and you prove that, by God, you got a map of spheres which is injective and continuous, and therefore, by invariance of domain, it's a homotopy equivalence. And that homotopy equivalence, once you write down the vibrations and see what I'm talking about, immediately gives that this map really does map gamma i's to delta i's, and you're done. And it's very quick, but it's actually not very hard. Questions?